Okay, good afternoon, everyone. Welcome you all to the last sessions for today. So today we're gonna have a talk on how you can make your LLM team for inference and when it's having more resource hog. Before starting, let me just go through with like how the agenda look like for today. So we'll be starting with very basic, like what are the LLMs, then we're gonna move to why, maybe we will go to the history of it, we will jump to the transformers, and then we're gonna move towards like what make your LLM a resource hog, and then how we need to fix it. Later on, we're gonna move towards the three focus area that we have analyzed, and we're gonna break them down. Later on, like we do have some architecture, some good benchmarks and results for you and key takeaways. Before starting, let me introduce myself. I'm Aditya Soni. I'm one of the SREs working at Forrester. Apart from that, I'm one of the CNCF ambassador. Before this, I worked at Red Hat and more. With me, I have Hrittik.
So hi everyone, I'm Hrittik Roy and I'm a platform advocate at vCluster. Apart from that, I'm a CNCF ambassador and a Google Venkat scholar. So I've done a couple of certification and most of my times are focused on figuring around Kubernetes, LLMs and all. So LLMs are everywhere right now and it is called the brain behind modern AI. So every time, every day, we interact with them in various ways, like if you are using a chatbot, if you are talking with a lot of ChatGPT and all those things. So LLMs are everywhere and they have a lot of more common use cases over the hype. So it's implemented in your research cycles, revenue gains, cost savings for sure, when you are optimizing costs around different sectors. And the basic architecture of LLMs is mostly like where we have a couple of things. So as you see, the client and response. So whenever you go and interact with ChatGPT, you just add a text or something and get a reply. Maybe it's a video token or an audio token or a text token. It can be anything. But what you are expecting from LLM is a response. But it is very simple to think that it's giving, but at the background, there is so many things happening, including there is a tokenizer which breaks down your text and queries into tokens. Then we have router batcher, and then all those KV caches are stored. And at the end, there is inference happening. And the pros of inference is like you are getting a response through LLMs where they are going through their previous batch data and trying to find similar tokens which can be equivalent to your response. And then you are being served with a model and there are different weights and all those things that you have. And lastly, your response is there. So the history of LLMs starts from Ngrams, and then in 2017, there is something called transformers, which changes how everything works. And now we have big data sets and big large language models, and something like ChatGPT 4, ChatGPT 5, and all those things are there, which are helping us every day. So let's understand why is the transformer puzzle so important? Because after transformers, you can see there are so many new LLMs. So whenever we want to train or fine-tune something, we want massive parallel computation. And for that, there is high-dimensional data matrix multiplication, which we are doing. And transformers are a different form of architecture, which helps you to build those and reduce your training time so that you have better and faster training and inference loop in comparison to other architectures which were there. So how transformers require GPUs? Like GPUs are built for parallelism, so you can do that easily. But CPUs are for sequential logic, because CPUs can't do 175 billion maths per second because of the architecture they are based out of. So this is a simple architecture about CPU versus GPU. So as you can see, there is a control logic over there and a lot of ALUs over there. So CPUs shine in preemption. So you can start a task, stop a task, you can put the task in the queue and then keep on doing that repeated across different type of tasks. But GPUs are not for that. GPUs are meant to do one thing very good, that is matrix multiplication again and again and again. So your control logic is very less, but there is a lot of ALUs which helps you to focus on doing one thing good without any cache. So now as we understand GPUs are very important, we see that everyone is launching and creating pools that helps you to do more AI/ML workloads. AWS launched 100K nodes per cluster support, by which you can have massive and parallel computation across different geolocations in one cluster, so you can have very big inference tasks and training tasks. But the problem is, increasing GPUs is not always worth it, because creating more GPUs and it doesn't help you at that way. So the optimization is more important, as you can see over this graph, as lower is better. And the other problem is, it seems to be good until it's not. You have a lot amount of GPUs. Everyone has more resources right now. They are procuring GPUs and all those things, and it's easy to get them. But the problem is, like, you can get a couple of sets, but as your inference task increases, getting GPUs become harder because there is a huge amount of GPU shortages. So the goal right now is to have GPUs at first, but then optimize it as well.
Okay, so as you see, like currently the whole world is running on AI. Maybe like you all have already gone through with all of these. Like you must be using all of these models called OpenAI or Meta or Microsoft, or maybe from AWS Bedrock, you must be using all of those. But if you see, it's always grass is on the greener on the other side. But there are a lot of challenges that can come with those LLMs. So there can be unpredictable GPU saturation, memory leak, latency, token overutilization, or you can have maybe your LLM that's scaling, and then you are facing a lot of issues. Maybe you are having excessive of cache that has been stored but not has been retrieved. So these kind of issues that you can have with the LLMs. So that's how, like previously, like you said, like okay, things are going well, but if you just come to the challenges and you feel like, oh, like I'm fine, it's everything is fine, but things not like that. If we start very basic about understanding LLM or inferencing, so that there is a three-phase, I would say, for this. So the first one is training, then we have fine-tuning, then we have inference. So it's like you train the model, you tune it according to how you want it work, and then you're trying, or maybe you are trying to run it so cheaply anywhere. So that's what the three phases includes, and today we are focusing on mostly on the inference. That's the everyday workload you are just running. You have a lot of clients, those are requesting those requests, but your inferences is going high. But at the same time, that high throughput you're not able to serve, and that's how your resource hog is there. So that's what we're trying to solve today, and we'll understand that. In this KubeCon itself, from the keynote, we just captured this particular screenshot. So if you see, everything currently focused on the footprint of inference computing. And that's why it's so important to focus on this talk, and maybe later on, if you are building any AI agents or building any LLMs, so on that time, you might face the same issues. Okay, so what inference is? So inference is basically when your algorithm moves and it starts to produce some sample results. So that's where inference actually comes in picture, and it actually solving a lot of business critical problems for you. So that's what it is. And if you see, because we have a lot of clients and they are just coming and they're saying like inference is painfully slow. And what does mean? So maybe their model takes too much time to respond because you have already sent a prompt, or maybe you are trying to build something, but that's too much time to respond. And then there's latency, so that is high, or maybe whatever response you have sent, so you have not got the particular request not served. Or maybe your GPU performance is inconsistent. So most of the time you have a lot of GPUs, but another time you see, okay, so I had GPUs, but why I'm not able to serve this particular request now? Okay, so that kind of issue you might face. Going forward, you might face issue with the throughput. So how that request per second, or maybe like when you have a lot of maybe 100K clients, or they are sending the request at the same time, so how that actually can be handled. So that's all I would say, like the inference issue, or when you say it's basically working so slow. So these what kind of issues can face. If you see where LLM inference actually comes inside the cloud native AI stack, so this is one of the white paper, and that's from we took this particular image. And so if you see, there are a lot of like starting from hardware, infra, platform, ML workload, and more. So the ML part that's coming from your ML lifecycle, and that's where your all of the AI ML or LLMs comes in picture, and that's where your LLM fits in. So you might have the whole infra, you might have the whole hardware that's in good shape, but if you're not work towards these kind of issues, then you might be stuck later on. Okay, now let's come to the point why inferencing so hard. Because what are the issues that can come when you're inferencing, and why it's so hard. So today we're gonna focus on major some things, but if you see every day, whatever task you are doing, so that's using the inference only. So either you are generating some aesthetics, analytic properties, okay, so maybe you want to do research on particular topic, and then you are just trying to get more results, or maybe you are using a lot of tokens. So on that time, this kind of issue can face, or maybe you are making some video generation from a SaaS platform, you are trying to build some images, something like that. You are trying to do some real-time trading signals, or you are doing vibe coding, something like that, or if you are trying to do some predictions over there. So each and every task actually use the GPU utilization, and that goes higher. So once these go higher, and that's where like inference comes in picture, and you need to fix that first. So the major things that we're going to focus today is the first one is the KV cache, and then GPU underutilization, and how GPU increasing the GPU is not always helpful. So if you see here, like we do have the compute resources and time per request, but if you see the idle and active CPU or GPU, those are, it's like you think like, okay, I do had some GPU or CPU, but when you get a lot of requests, it don't perform well. Okay, so let's understand first what is KV cache is. So KV cache is nothing, just you can take it as it's a key value. So KV means key and value. So whatever input sequence or the prompt you have got, and it uses some token, and it first checks, okay, so do we have the same cache available, or the same data is available? If it's available, it retrieves the same thing from the cache. If it's not, then it go to compute, or maybe it will try to do more pairs with those cache, and once that is done, it will just, after computing, it will just store those cache, and it will generate the token again. So that's how the cache generation actually work. But if you go deep dive inside this, so there are a lot of steps that actually takes in place. So without cache, actually you take, it takes a lot of time, it takes a lot of energy from your whole infra or the whole GPUs things you have, or with cache, it's not take all of those quantization, because we do have like this particular algo called pagination. So that's how actually it calculates all of those cache that it needs to perform. Okay. And one more thing is here, like as we said, discussed previously, like GPU is not always fully utilized, because you feel like you are using GPU and that is already fully utilized, but that's not always the case, because you can monitor it, you can improve it, okay? And at the same time, we're gonna discuss later on, but I'm just giving a slide, like you can maybe have some profiling inside your code, and you can check, okay, how my code is behaving. So that way you can check how many GPU you are utilizing and how much you are wasting. Okay, so now we have focused on the issues like KV caching or your GPU that's not fully utilized, but how that can be solved. So let's first do the first thing, that is the, I would say, KV cache. So you can actually optimize your KV storage, and you can actually work on the retrieval part of the same. Then the next thing comes the GPU. So you can improve how your GPU basically working, or maybe you can batch, you can share those GPUs, you can use different schedulers for the same. Then we have some observability stuff. Okay, so what's the KV cache solution? Like we actually configured, and that's actually working fine for us. So the first one, I would say the vLLM. So vLLM do have some patch attention, continuous patching, and with that, with the help of that, you can have around 3x of throughput. Then you can have LLMD, or maybe you can combine both of them. We do have some architecture, I'll show you later on. Then there's another solution with GKE that's actually published by Google Cloud, I would say tiered KV cache. Then you can store some cache that's locally, and that can serve your responses better. Let's first come to the vLLM one. So in this VLLM, we do have 3 common ideas. So you can do the continuous batching, you can do the page retention, or you can optimize your KEDA kernels. So if you see here, like whenever as you're requesting any new cache to be made, this is how the whole process looks like. So basically, the first thing is like your whole cache. If you see here, like we do have 7 cache states, and it looks for all of the slots that actually can be filled with all of those key and values, and then accordingly it do create those pairs. But once you can move to the VLLM, so if you see like existing system would have a lot of higher bandwidth, but if you go with the VLLM, then you can see like the performance was better, and that's how it actually uses a lot of less KV cache, and you can reduce that. Another thing is like you can go with the VLLM plus LLMD. So it's like you can create, like you can put your VLLM in the, I would say, VLLM fleet. At the same time, you can use LLMD. And with help of that, you can use KV events, or you can use your cache manager to serve all of those requests with the help of any inference scheduler. Okay, so once you have already configured all of this, so you have to focus on which type of scheduling you have to focus on. So there are a lot of types of scheduling are there, but the one that worked for us is the precise scheduling, and with help of that, we have got time to first token. Those are very, I would say the second was so less for the mean also, and the P95 or P90 values also. And if you see like the output, how much tokens per second we have around maybe gathered over here, so that is also quite good.
So now the problem is the GPU part of the puzzle. So GPUs are everywhere in every layer. So what we do is like, one second, yeah. So now we have a lot of requests coming together, and analyzing all those requests together is very hard. When you batch everything together, there is a better parallelization which is happening, as GPU are not very sequential on this order, so you can get a higher utilization. So if your GPU is not saturated, you can double your batch size and the learning rate, which helps you to get more response together in order in comparison to waiting for response one after another. And now, apart from the batching, there is also about how you share your GPUs. So generally, there are a couple of ways you can do that. There is the time slicing, which acts as a fundamental and a way where you can do it any GPU. But again, there is something like MIG, which is not enabled in all those type of GPUs you have. So these are in A100s, H100s. And then there are more modeling scheduling tools like KServe, which is from NVIDIA, which helps you to do it in fraction. Each of them has their cons and pros. But when we think about time slicing, it's just software multiplexing, where it feels like you are using the GPU sequentially, but actually that's the only case because you are not running parallelly a lot of tasks. With MIG, it's a better way to do that, but again, the problem is like if you have a strong hardware like A100, then only it's supported. You can't get in any GPUs you have. But the disadvantage over there is it's sometimes cheaper to get more GPUs which are less powerful than to get a expensive GPU like A100. And then at the end, there is something like KServe, which is from NVIDIA, and it helps you to schedule in fractions. For example, if there is an inference and fine-tuning and pre-tuning task, you can isolate and fractionally describe how much you want in each of those parts. For example, you can have 70% in inference, and all of those things together come into a picture where you have a lot of GPU nodes, a scheduler in between, and then you can have different tenants over here. The problem over here is like, you can have multi-tenants consuming a single GPU, but what if you want more isolation like CRDs and all those, and unified developer experience? So here where something like vCluster comes to the picture, where you can have multiple tenants into the same hardware cluster, and each of those tenants can have separate CRDs, separate user access, so you can share your GPU across a single node and across different clusters. And at the end, your architecture looks something like that, where you have different clusters for your different teams in a single cluster, and you're utilizing GPUs at the full instead of having fractional utilization. When we talk about the observability solution, so there is a caching solution, there is optimizing your GPU, and then there is the observability solution. Observability comes as a fundamental layer in all those background. Why should we observe anything? Because you can focus on how you are tuning your GPUs. You focus on model performance. Is the model performing well for your outcomes or not? And then there is benchmarking your cost and performance, which is very important to decide how you want to inference and how you want to scale. So a lot of times, a very bad practice and a very common practice is people measure the GPU once, but it's not very helpful. As we can see that we were training a RNN, and a lot of times GPUs drop mid-training. It is not because it's not by nature, it's because you can have data loading bottlenecks, inefficiencies, and all those things. So measuring always is helpful. But apart from that, there are other reasons as well. So with time, you can find a lot of GPUs become inefficient, and sometimes this is hardware related, sometimes this is the application related. So there might be a code or a distributed bug which reduces the GPU performance and increases the latency. And it creates a load imbalance between different GPUs and can create a configuration issues across those. So as you see over here, you can see one GPU drops to 0 while mid-training, and the other handles all the computation. While you have a distributed architecture, this is not an ideal outcome you want. And lastly, there can be a lot of cases where the GPUs are overworked for a couple of them, but the rest of the GPUs are not handling any pressure from your inference. So that becomes a problem, and it helps to observe those, because at the end you want your evaluation phase not halting the training and all those things, and you don't want inefficient pipeline scheduling for across all your clusters and all your workloads.
Okay, so like as we already know, like why observing the things is, or maybe observing the GPU is always helpful, but how you do that? So for doing that, like you do have multiple options, but one of them is like you can use Autel, and Autel do have one of the feature called profiling. Recently they have merged it, and so you can just go to Autel EBP profiler. So what is profiling? So profiling actually help you to understand how your code is behaving, or which part of your code is consuming high GPU, lower CPU, or something like that, and then you can fix them. So you can see in this particular image, so you can actually check like how much a particular thread is using the CPU and maybe GPU or all other samples. And you can actually go with the distributed tracing. You can actually trace each and every request that you have got, and accordingly you can make your decisions. Once you trace your LLM application, that actually shows your how much token it has consumed, how much token you have remained, and a lot of stuff, because this is something like it goes inside the code. You can actually, there's a SDK, you can integrate it, and then that's how you can visualize this stuff. So after doing all of this stuff, it actually helps you to reduce a lot of cost, because once you deploy your LLM application, the cost is around maybe $50K, and once you dig inside all of the costs, it can actually, you can reduce around 20% of the cost. And this is something that actually gone from Grafana. So what they have observed is like when you use profiling, so it actually, you can save around this much of cost while the profiling is there. So it's all about like maybe while you are developing the whole application or while you're deploying the application, so you have to maybe take care of these things. You can check like how much CPU or uses per token is there, or maybe the latency per request, or while deploying it, you have to check on the how much GPU utilization is there, or the how much efficiency it's working.
So now those are the simple steps which you can implement and save some cost. But now as we go on distributed inference across different geolocations and different providers, because now a lot of new clouds are coming into the picture where you can get cheaper GPUs, there are other challenges that comes into the picture when you scale. First is distributed attention kernels. So you can have kernels which enable more GPU inference faster. And then the biggest challenge to solve is like having KV cache across different nodes. So storing cache across a single node is easier than distributing that. So those type of challenges are where working helps you to store and distribute it. Caching helps you to get faster inference for your workloads. Apart from that, communicating graph capture through NCCL and KEDA hooks helps you in a way where you can have faster pipelines and faster inference. And there are other ways, like you can have pipeline and mixed precision for inference stages. So it improves the overall performance and the inference capabilities you have. Going further, GPUs are built for parallelism, but when you use sequence parallelism, you can have and use long sequences for your entire data set. And as we were discussing about Volcano or other CNCF project sets, which helps you to have batching strategies. So you can dynamically batch your workloads together, which are similar and different types. So you can have lesser latency while increasing the overall utilization for those. And lastly, MOE routing is also there, which helps you to share across different GPUs. Right now, the problem is like we are bringing bigger clusters together, and some of them are together and some are different and saturated across different geolocation. But having a cross node-to-node communication while you are sharing your GPU, where each of the GPUs are focusing on single areas of performance, it helps you if you can enable MOE routing, which is very complicated at all. So overall, you can start with focusing on 3 areas, like KV caching, making it tiered, making it distributed, then focusing on how you are sharing your GPUs, maybe through different schedulers or different ways. And lastly, observing and profiling all of those things together helps you to achieve a better state for your inference performance and cost.
So, yep, with that, you should catch smarter, scale better, and see everything what's happening within your code. And with that, like, we are good with this talk. You can connect with us on our handles, and if you have more questions, we are here to chat about. Thank you.